Hi everyone, I am Tousif Islam. I'm a fourth year PhD student at the CSC here and at the Department of Mathematics. So in this particular project, what I'm doing is I'm building a high performance framework for differentiable gravitational waveform models, and I'll explain what I mean by that. Okay, so um, this talk, I'll first describe what is gravitational wave modeling and what we generally do. And then I'll move towards the second part of the talk where I'll describe what I'm doing while I'm building differentiable gravitational waveform models and how that would help. Okay, so what I generally work on is binary black hole monitors. What it means is that there are two black holes which often merge against each other, and in that process, it emits radiation in forms of gravitational waves. And those gravitational waves are then detected on Earth, and we analyze that signal and try to understand about the black holes and how they are formed, what is their distribution in masses, spins, and also we'd like to know how gravity works and so on. So in the binary black hole mergers, when they merge, they go through basically three different stage of evaluation. So they start with the spiral where the two binary black holes are far apart from each other. Then the distance between these two black holes that shrinks, and at some point they just merge, form an unstable black hole, and then that emits further radiation, and finally it just rings down and comes to a stable stage. And in that process, it emits radiation that is shown in the left panel in the lower part of the figure, which kind of increases in amplitude and then it decreases and comes down to zero. Okay, and what I show here is one particular signal for one binary black hole merger. And then what we do is we simulate this kind of signals using computers. We do it for many different binary black hole configurations. And the hope is that once we have many such simulations, then we would use those simulations to build a model, and that model will help us to analyze the actual signal that we detect on Earth and help us know about the black holes in a better way. So this is basically kind of a summary or a zoo of different kinds of binary black hole waveforms that we can have. And with these waveforms, what we typically do is that we populate a parameter space that is shown a representation of what I mean is a two-dimensional parameter space here, and then we have different binary black hole simulations which are shown by these dots here, and that kind of scattered through the parameter space. And once we have many such simulations, then we use sophisticated interpolation techniques such as Gaussian process regression or splines, along with the similar value decomposition and so on, to like have a model that can give a waveform at any point in the parameter space. And we do that using reduced order representation, and we call these models the surrogate models. Okay. However, the surrogate models that we have, there are certain limitations. So one is these surrogate models, by the way, they are very fast. While a numerical simulation takes a day to a month, this surrogate model can generate the same waveform in less than 1 second. However, these models use on CPUs, and they can only generate one single waveform in 0.1 second. But if we are doing a Bayesian framework, Bayesian analysis of the signal, we generally require 10 to the power 5, 10 to the power 6 waveform evaluation. So even 1.1 second sometimes can be expensive. So there should be some framework that can give us waveforms much quicker. But also there are often situations where we need to have different have a need to know the gradient of these waveforms as a function of the parameter space. It could be the masses of the black holes, the spins of the black hole, or anything else. And in those cases, the only way to do is using numerical techniques such as finite difference methods. And these methods are not always stable, especially if you have really long signals and then you start using finite difference methods, then your errors keep accumulating, and then at some point it might diverge. And also, I mean, even if it doesn't diverge, you get really high error. So we need a framework where we can speed up our waveform generation, but at the same time, we can also have differentiate and also able to have differentiate the waveforms. So what I'm doing is I am basically building the surrogate models in a differentiable framework. And for that, I'm using this Python-based framework called JAX. And this particular framework provides many um, features that we want. For example, it uses just-in-time compilation, where the compilation happens while you are executing the program, and this provides like quite a lot speed up compared to a usual Python program. It also automatically vectorizes your codes, and that way it can also handle multiple operands. And then finally, it automatically differentiates your functions and your codes, because you write all of the codes in JAX, and however complicated your codes are, they are basically a combination of arithmetic operations, for example, addition, subtraction, multiplication, division, and a function, and different functional forms, for example, log or exponential or so on. So the program might be really long, complicated, but at the end, it's basically a combination of all of these. And what it does, it applies chain rule on every piece of your code. And applying that again and again, it knows the differentiation. It forms its own function form for the differentiation. So it knows what should be the differentiation without doing the numerical differentiation itself. And finally, when you do all of this, you can also parallelize your code, which is kind of somewhat connected to this automatically vectorization, and that's how you can also gain speed up. So here is a very small snippet of how it does that. For example, if you look at, if you see my cursor, what it does, you define some array, and then you just do jax.grad, and that gives you, or a function, that's grad.function, and that gives you the automatically differentiable functional form, and which you can use anytime you want to have a differentiation of your functional form. Okay, so what I'm doing here is that I'm using JAX, and then this state-of-art Python package called GW Surrogate, which is one of the very popular Python package where we put all of our surrogate models that we are building, and this is used for the analysis of actual gravitational wave signals. So I'm writing models that are in GW Surrogate. I started with one particular model called the NR Hybrid Surrogate 3DQ8, and I have basically wrote a JAX version of that in this particular repository here. And now like this GW surrogate has 6-7 different models, but I'm starting with one model, and then the plan is that to have more and more models in this JAX framework. Okay. Then moving on, this is what I'm showing here is a comparison between the JAX version and the non-JAX version. So in the left panel, we show the waveform, and you have your the blue is the non-JAX version, the actual waveform that comes from GW surrogate, and then the orange is the JAX version of that. And what you can see is that here is that they are basically on top of each other. Uh, and with the right, I show the difference delta H, and which you can see is currently at the order of 10 to the power negative 4. And this way, while GW surrogate can give you one waveform in 0.1 second, because now I'm using JAX, I can provide, generate 1,000 waveforms in 1 second or less than 1 second. So, and this uses GPU. So that's the speed up I get. But at the same time, what I get without any cost, that is the automatic, like the differentiable waveforms whenever I want. Okay, so I think I'll just put the summary and stop here. So what I have done is that I'm developing circuit models that are automatically differentiable. And this includes writing codes in JAX, which is a Python-based automatically differentiable framework. And there's this particular surrogate that I'm building. This retains the accuracy, it has this almost same accuracy of the traditional models, while it's speeding up the waveform generation part and also providing the gradient free of cost. So I'll stop here. If there are questions, I'll try to address those. Thank you.
Any questions for Tousif?
I have one. So you said you use just-in-time compilation.
Yes.
I was wondering what platform did you use it on? So like operating system and then language.
Okay. So I'm using, so this is all written in Python. And the good thing about JAX is that yeah, it doesn't really matter on what operating system you're using. You can use, I think you can use JAX anywhere you want, but it has both CPU and GPU support, but I'm using GPU because only in GPU you'll get all of the speed up that you are doing. But this just-in-time compilations as well as the automatic vectorization and differentiation, these are all done under the hood by JAX. But to run the JAX, this is a Python-based program, so you have to use Python.
Okay. Thank you. That's awesome.
Yeah. Thank you.
Any other questions in the audience? Okay, I have a quick question. Tousif, maybe if you wanted to elaborate a second on how the gradient can be useful for parameter estimation, which I think some people are interested in.
Yeah, sure. So what happened? What Scott meant by parameter estimation is that when we get a signal like that, we do not know which binary black hole system has generated this particular signal. So we have models, and we want to use that model to get the best fit parameters in some way, and for that we use Bayesian inference. Now, in the Bayesian inference, we have different algorithms. For example, people use Markov chain Monte Carlo, or people also use nested sampling. So these all algorithms are, while they are efficient for small dimensional parameter space, for binary black hole systems or systems where you have 10, 15 dimension or maybe even more, this Markov chain Monte Carlo nested sampler, it becomes harder for them to actually find the best fit parameters or explore the parameter space properly. So in some way, this is kind of an optimization problem. You are basically trying to find the set of parameters for which you get the maximum likelihood, or you are minimizing the loss. So if you know the gradient of the functions you have, or the function you're trying to optimize, then you can help your sampler to follow that gradient and then find the optimal position. So if you want to do that, then you have to basically generate the waveform, but at the same time know the differentiation of that waveform. And that becomes tricky if you do not have an automatically differentiable waveform. But if you have one, then you can use newer or more state-of-art techniques, for example, Hamiltonian Monte Carlo, where where you sample your parameter space while doing deviation inference, knowing the gradient. So you follow the gradient there. And if you have automatically differentiable waveforms, then you can basically use those techniques, and that will give a lot of speed up in your Bayesian inference. So that's where the real benefit of doing this will come.
Great, thanks. Okay, let's thank the speaker again.
Thank you.